Welcome, everybody. I'd love to introduce Shyue Ping from UCSD, who's been working at this intersection of materials design, applying machine learning to it, but really like in a physically grounded manner. Yeah, welcome, Shyue.
Thank you, Greg, and thank you for the opportunity to give a talk at Google X. I'm really happy to be here. So I'm a professor at the Department of Chemical and Nano Engineering at UCSD. So today, my talk will be on foundational potentials for massive scale materials design. All right. So usually when I give a talk to an external group, I like to give a brief introduction about my group. So my group is called the Materials Virtual Lab. We are a pure computational materials lab that aims to bring forth a transformative leap in the speed and scale of materials design through data science and AI. So these are what I call the 5 pillars of my group. So fundamentally, we are still material scientists. So usually we start from things like the fundamental equations of science, for example, the Schrödinger equation or the equations of thermodynamics and kinetics. My group is an expert at high throughput automation. In other words, we write software frameworks that allow us to automate electronic structure calculations such that we can generate a huge amount of data. And through that, we develop databases of material properties. All right. Now, once we actually have the data, the third pillar of my group is actually in terms of learning, right? It implies not just the application of AI and machine learning to models to really build predictive models based on those data, but also in terms of data mining and screening of new materials from that data, right? Now, in terms of application, we are a bit agnostic, but there are 3 major areas that my group is known for. One is in terms of energy storage. We discover things like lithium and sodium ion batteries. Another area is in terms of energy efficiency. We look at materials for phosphor, such as phosphors for solid state lighting. And also we work on materials for extreme environments, such as aerospace alloys. Finally, the 5th pillar is the community. We are big contributors in terms of open source software as well as data. I'm going to talk a little bit about one of the big projects that we work on called the Materials Project. And we develop things like open APIs to our data as well as do various outreach events. Now, I'd like to start my talk with a very famous quote from Paul Dirac. This was in 1929, where he said that the underlying physical laws for basically most of a large part of physics, as well as the whole of chemistry, were already completely known at the time, and that approximate practical methods of applying quantum mechanics should be developed, okay? So what this means that even in 1929, Paul Dirac already foresaw that we already have the equations that is necessary to do most of material science, right? The only problem is that that equation itself was too complex to solve, even today, for any practical system. And what we really need are approximations to solving quantum mechanics, okay? So that basically is a reality today. Today, we can already solve quantum mechanical equations to some extent. So the way that this works is you start from the Schrödinger equation. You usually use some approximation, such as Kohn-Sham density functional theory, where you essentially map the many electron system to some functional of the electron density. And what you then do is that you plug it into a computer. And after you do some analysis and processing, essentially what you can get out at the other end are material properties, okay? So you can predict things like the phase stability of a material, the diffusivity of a material, its electronic structure, things like the band gap, mechanical properties, and many, many more, okay? So what this means is that today we can predict material properties before we even step into any lab to actually try to make them, okay? So the nice thing about quantum mechanics-based computations is, first of all, because we are starting from the fundamental equations of physics, this is universally applicable to any chemistry, right? So that it is not a custom model that is for some select structure or set of elements, okay? We can work across the entire periodic table. And of course, any form of computation is inherently scalable. So with the powerful supercomputers that we have today, we can already do very large-scale data generation using this kind of computations, okay? So back in 2011, 2012, former President Obama started what is known as the Materials Genome Initiative. And one of the key projects that was started under that Materials Genome Initiative is called the Materials Project. And this is a project that I have been proud to be part of since its inception, okay? So the Materials Project, which some of you may be familiar with, is basically an open science project to make the computer properties of all known inorganic materials publicly available to all researchers to accelerate materials innovation, okay? So this is the link to the Materials Project. It is a free database that you can anyone can sign up and log in. And today, if you go to the Materials Project, you can see that we already have quite a fair bit of computations. We have about 150 to 200,000 materials computed, and we have a lot of different properties that are already within the Materials Project. And the total number of users is on the order of 500,000 users from all over the world, okay? So based on all that, you might think, well, why don't we just continue on and just use quantum mechanical methods and way into the future, right? Why do we need to think about AI and machine learning, right? And this is a nice plot that I like to show that shows you the problem in some way, right? So this is what I call the data history of the Materials Project. Essentially, it is a plot of the total number of entries in the Materials Project for different types of properties as a function of time, right? And what we see is that in the past few years, we have sort of stagnated in the total number of structures and energies that are being added to the Materials Project, right? So in some way, we are running out of things to compute, but yet in certain instances, we have a lot more to compute, but we just couldn't do it, right? So for example, if you look at things like the elastic constants, we only have on the order of about 13,000 to 20,000 elastic constants computed in the Materials Project today. And the main reason is just because to compute elastic constants is a much more difficult type of computation, right? So it involves many, many steps, it involves supercells, and that in itself is a problem, right? And it is just simply too expensive even for us to scale to 200K materials today, all right? So, and the reason is really very simple. All quantum mechanical methods today scale at least on the order of n cubed, where n is the total number of electrons. What this means is that even with very powerful supercomputers, we are really looking at being able to simulate on the order of less than 1,000 atoms, right? In the real world, that is nowhere near enough for you to simulate real world materials, right? Real world materials look more like this big thing that you see on the right here, right? You have grain boundaries, you have many different type of elements, you have defects in them, disorder in them. So you really need to be able to simulate things like on the order of millions of atoms to address many, many different types of materials problems, okay?
So question. I mean, just to get an idea of the kind of approximation that DFT performs and its limitation, because I mean, it's looking like it's assuming some homogeneity in electron distribution, which for these complex materials does not hold at the scales you care about.
No. So DFT does not assume homogeneity in the electron density, but rather it is a local based approximation. In other words, it assumes that the energy at every point in space is a function of the local electron density at that point. And then what it does is that it maps the energy and of the homogeneous free electron gas for that particular density to that space, right? So that is the approximation that's being made. It is a fairly good approximation for the most part, especially for some certain types of materials like metals, okay? But I would say that the scaling problem is independent of that. The scaling problem is just all the DFT methods. It is not just DFT, but rather even higher order methods. The scaling is just on the order of number of electrons, right? And it is n cubed, right? It's a power law, right?
So
So
let me get this, because this seems like an important to capture. You capture the complexity of this problem. It's
mhm.
Is it a problem that the functional form required, like, is a simpler form, and in reality, the dynamics more complicated, or it's simply dependent on much more than electron density for all these scenarios?
It is dependent. Just so there are accuracy that you lose from going to the electron density. Yes, that's correct. So there are certain types of correlated properties where you really need to model the full many body, many electron system. But I think for the most part, even for properties where the electron density approximation is a reasonable one, just solving the electron density equations, that is a n cube process, or at least n cube, right? There are certain methods which are more accurate, which are n to the power 6, n to the power 7, much worse scaling. So
Okay, so now we should be thinking of, you're saying number of atoms, not number of electrons. So we really should be thinking.
no, we are thinking of number of electrons, right?
Oh,
So,
is
but of course, yeah, but number of electrons is of course somewhat correlated to number of atoms, right? So, but it is the number of electrons.
Okay, so to what extent, I'm trying to understand the complexity of the material. Like, what aspects of the material's complexity really drive this? Because thinking abstractly, if I had a cloud of electrons, I'm done. I have a single function. It shouldn't scale unless my intuition is wrong.
Yeah, so definitely it is dependent on the number of electrons, but more accurate to say, the if you are thinking of in terms of periodic table complexity, it is dependent on the number of valence electrons, because most of the time the core electrons don't really participate in the in the anything you care about, right? Like, for example, if you are modeling a chemical reaction or bonding, typically typically only the outer shell of the atom actually participate in those kind of bonding. So it is the number of valence electrons. So as you go down the periodic table, that number increases somewhat, but not as much as you would think if you model the entire full set of electrons. So
That's good. Thank you.
yeah. All right. Now, today, there are a couple of different methods in which we do computational materials design. Okay, so QM methods is basically right here at the bottom. It is a trade-off between essentially transferability, accuracy, and cost. What it simply means is transferability, meaning whether can I explore the entire periodic table, or am I limited to some subset of structures or elements. Accuracy really means how accurate the predictions are, and cost meaning how expensive the method is, right? And cost is actually important because cost affects the length and time scale in which you can simulate. The more expensive the method, the smaller the length scale, or the shorter the time scale you can simulate, right? Because the computations are just a lot more expensive. Now, quantum mechanical methods, very transferable, very accurate, or at least as accurate as any method that we have today, but they are very, very costly. Now, there are things called empirical potentials, which are essentially just parameterizations of the potential energy surface of a material. These are a lot cheaper, which allows you to get to about micrometer timescale or microsecond timescales. But they are not transferable in the sense that you always custom make an empirical potential for a single system, and the accuracy also drops significantly compared to your quantum mechanical methods. Okay, and of course, on the other end, you have your continuum-based model, where essentially you can simulate things of any size for the most part, but again, you lose further in terms of transferability and accuracy. Now, today, with machine learning, we can build what are called machine learning interatomic potentials that essentially address a lot of this trade-off to some extent. We still get the cheap cost of interatomic potential. We do lose it a little bit in the sense that they are still a little bit more expensive than empirical potentials. And you gain, but what you gain is a little bit more transferability, and you get accuracies that are very, very close to what you will get with quantum mechanical methods. Okay. And finally, I will also talk about foundational potentials, which are essentially what we call universal machine learning interatomic potentials that essentially still maintain somewhat the same cost as empirical potentials, but now you get back essentially almost all of the transferability and still keep most of the accuracy. Okay. So this is my talk outline. I'm going to, in order for me to get the foundational potentials, I really need to talk a little bit about what machine learning interatomic potentials are. Then I talk about the concept of behind foundational potentials. Then I want to spend a little bit of time talking about our recent efforts in data and software for foundational potential development. And I want to show you that this is not just all theoretical work. I want to show you some of the applications, very practical applications in materials design that we have been doing, and also some perspectives on where the future directions are. Okay. All right. So the first thing is on machine learning interatomic potentials, or MLIPs. So one of the things that I want to state outright is, despite all the hype about AI in material science, people talking about, oh, I've been using AI for experimental characterization, interpretation, or AI for materials generation or whatnot. Machine learning interatomic potentials are the most impactful application of AI in material science today. Okay, so what this simply means is that this is the most successful demonstration of where a machine learning algorithm or machine learning models have had an impact on how we go about simulating material properties, and it is robust, and it is a way that we have demonstrated real-world impact. Okay. So what is a machine learning interatomic potential? It is essentially a parameterization of the potential energy surface using machine learning models. Okay. So the potential energy surface of any system of atoms is just basically a mapping of the energy and force of each atom to the position of all the atoms in the system. Okay. So this is a very simple concept. And machine learning interatomic potential, conceptually, the way it works is that it takes the local environment around each atom, it then maps it to some local environment fingerprint, and then a machine learning model is then trained to map that local environment fingerprint to the potential energy surface. In other words, the energy of forces. Okay. So all the machine learning interatomic potentials, the local environment ones work roughly the same way. Essentially, you are doing an expansion of the many body interactions, and then those fingerprints represent these many body interactions, and then you use a machine learning model, and it really doesn't matter what kind of machine learning model you use. There are people who have used just simple linear regression, you have your kernel methods, you have your neural networks, and they then just essentially map that local environment fingerprint to the potential energy surface. Okay.
Question.
Now,
is the computer using a simplified simulation, or are these DFT simulations for various points in the space?
They are done using DFT for the most part. So yeah.
So we should be imagining a sparse sampling of the potential space using DFTs, and then you fit that using ML.
Correct.
Awesome.
That's correct. Yeah. So this is basically what you gain. Essentially, instead of this order n cube with quantum mechanics, essentially what you now get is basically an order n, where n now is no longer electrons, now it's really atoms with machine learning interatomic potential, right, in terms of compute costs. Now, so machine learning interatomic potentials are accurate, they are fast, and more importantly, they can be generated using automated workflows. Okay, so if you work on traditional interatomic potentials, you realize that typically fitting one is basically like almost an entire PhD of effort. Okay, so it's a black art, right? With machine learning interatomic potentials, essentially I can write a workflow like this. I can write a recipe, in other words, and typically, because my group is very good at writing software to automate calculations, we do this. And then essentially nowadays, I can generate a machine learning interatomic potential for any system I'm interested in within, say, a couple of days to maybe 1 or 2 weeks. Okay. And more importantly, machine learning interatomic potentials, they are much more accurate, right? So these are the traditional interatomic potentials. These are machine learning interatomic potentials. And they generally have about 10x better accuracy. In other words, 10x lower error in both the energy and forces compared to your traditional interatomic potentials. Okay. And with that, we can then begin to do very, very interesting applications. So today, most of the applications I'm going to show you are in the lithium-ion battery field. I do have examples from other applications, but I think for consistency, I want to just focus on our work in batteries. Okay. So one of the biggest topic in battery research today is on all solid-state batteries. Okay. So essentially, what an all solid-state battery is that instead of having a flammable organic liquid electrolyte, you are replacing the organic liquid with this solid electrolyte. Okay. And this is aimed mostly at addressing one key problem, right? I think you probably have heard a lot of news about all that lithium-ion batteries are catching fire in phones, in laptops, in planes. So with a solid electrolyte, what we are hoping to do is essentially we'll address the safety issue, and potentially we can also have architectures that are much more conductive, okay? Or much more energy dense, okay? Now, the problem is that with quantum mechanical methods, so one of the key properties that we need from a solid electrolyte is essentially it has to move lithium very fast through the material, okay? Now, with quantum mechanical methods, we have severe issues about simulating this ionic conductivity of materials, okay? Because of the high cost of quantum mechanical methods, the cell sizes that we can simulate are very small. I typically have to do very high temperature simulations, and because I only can simulate for very short time scales, and then I just extrapolate down the conductivity to room temperature, okay? And what you see here is essentially a work that was done in 2016, about almost 10 years ago, by my group. And you see that essentially we are not getting very accurate results, right? The green line is basically what we simulate. The red line is basically what the experiments actually measure. And what you see is that there is almost a 1 order of magnitude discrepancy between what we predict and what was actually measured in the experiments, okay? Now, with with machine learning interatomic potentials, now that has changed. So we can actually build machine learning interatomic potentials for any set of chemistries that we're interested in. So, for example, these are 3 different chemistries of solid electrolytes. And once we actually fit machine learning interatomic potentials, I can do much longer simulations. For example, I can do 1 nanosecond simulations in realistic conditions, like what we call an MPT simulation. And what we see is that now our predicted ionic conductivities at room temperature are a lot closer to experiments, okay? Previously, I was 1 order of magnitude off. Now I basically get right smack in the middle of the experimental predictions, okay? And the reason is twofold. One is because we can now simulate the conductivity down to room temperature, okay? So we get actual room temperature numbers, not extrapolated room temperature numbers, okay? And we find that actually one of the reasons why we have an over prediction is really because of this transition that is occurring at about a relatively low temperature of about 400 to 525 K, okay? So this is important because we are now finally able to simulate room temperature behavior, and that's basically what we as battery scientists actually care about, right? Not some hypothetical conductivity at 1000 K, all right? And we are actually able to compare that to experiments, and we see that essentially, even in experiments, you actually do see the same transition, and that transition temperature is actually quite close to basically what we predict, okay? Now, machine learning interactive potentials also has the potential to allow us to simulate other kinds of problems. So for example, one of the big issues in a lot of solid electrolytes is that the grain boundary diffusivity tends to be much lower than the bulk diffusivity, okay? And with machine learning interactive potentials, I'm not limited to now a cell of less than a few hundred atoms. I can do essentially much larger cells of thousands of atoms and create grain boundary structures and simulate what the behavior of atoms is at these grain boundaries, okay? So this is the grain boundary diffusivity in this specific solid electrolyte called LSTZO. Essentially what you show is that because of this strontium addition to this solid electrolyte, it has no lithium depletion at the grain boundaries, and because there are no lithium depletion, you actually maintain grain boundary conductivities that are similar to bulk conductivities, okay? And this is important because the original material that people work with, the solid electrolyte that people work with, is called LLTO. And in LLTO, the grain boundary diffusivity is 3 orders of magnitude lower than the bulk diffusivity. And that becomes essentially a resistor, right? It doesn't conduct lithium all that well once any grain boundaries are present, okay? All right. Now, despite the very huge impact that machine learning interatomic potentials have for the field, custom machine learning interatomic potentials alone cannot solve the materials design challenge, okay? There are 2 reasons, okay? One reason is the local environment MLIPs, they combinatorially explode in complexity with the number of elements, okay? So you imagine I'm building this energy expansion in terms of single body, 2 body, 3 body terms. If I have more elements, my number of terms, at least the 2 body terms, would grow as n choose 2. My 3 body terms will grow as n choose 3. And you can see why once we get to 4, 5, 6, 7 elements, this number becomes huge, right? So in essence, you can't really build a general potential using local environment fingerprints, okay? The other problem is because we are custom fitting the potential, even though I can build an algorithm to do this very quickly on the order of 1 to 2 days, it still relies on expensive DFT calculations, and the iteration speed is very slow, right? So in other words, what this means is that I cannot explore the entire periodic table with a custom machine learning interatomic potential, okay? So that was our state of the art in 2020. And back in 2021, where actually the Apple TV series Foundation came out, we thought about, we basically had this very, I would say, bold new idea, which is that why don't we try to build a potential, a foundational potential that essentially can cover the entire periodic table, right? So I don't really want to be fitting custom potentials for every single system I'm interested in. I want to be able to explore the entire periodic table, okay? Now that brings us to foundational potentials. And to build foundational potentials, we essentially have to look towards a different kind of machine learning architecture, okay? Now, message passing graphs are, of course, one of the most popular machine learning models today, okay? So I think Google was actually one of the main pioneers in developing all these graph networks and graph neural networks architectures. So essentially in a graph neural network or a message passing graph, you are essentially representing each atom as a vector of numbers, and the bond between atoms has also different vectors of that number, okay? So you are representing the entire material essentially as a mathematical graph, okay? And what you then do is that you pass messages between the atoms and the nodes, the nodes and the edges and the nodes, and so on and so forth, using neural networks, okay? And that is what essentially why they are called graph neural networks, okay? Now, it turns out that just simply using graph neural networks alone are not sufficient to represent a potential energy surface very efficiently. We still need to take into account, still need to combine that with essentially inspiration from our traditional interatomic potentials, where we include some expression that includes the many body terms, okay? So in this very, very first version of a foundational potential that we developed, we essentially just use 3 body interactions, and we call this architecture the materials 3 body graph networks, okay? Now, to train this first foundational potential, what we did was to essentially, we had this insight that in the materials project, we do have the data necessary to at least train a very rough version of a foundational potential, okay? So at the time, we have already performed around 100,000 DFT structural relaxations since 2012. That essentially gives us a data set of about 100,000 energies, about 10 million forces, and about 1 million stresses, okay? That data also encompasses interactions between 89 elements of the periodic table, okay? So in other words, this is true, complete universal coverage of the periodic table, right? We have almost every single element except for some of the radioactive elements that we don't care about, or maybe the noble gases where essentially they don't really form that many compounds, okay? So we essentially took all this data, we throw it into our M3GNet architecture and train a model. And the result was actually somewhat surprising to us at the time. We essentially found that with this foundational potential, we can already do quantum mechanics free structure, energy, and stability predictions, okay? This foundational potential can actually relax crystal structures to within about 50 MeV per atom of the DFT energy. The error in the volume is about less than 2%, okay? And we can make stability predictions by computing this thing called the energy above Hall. And the stability predictions from our foundational potential is actually in pretty good agreement with DFT, okay? Now take note, this is of course 2022 technology. Now we are able to do a lot better, okay? Now, once we actually have a foundational potential, we are not just able to relax and compute energies, right? We can now begin to do dynamic simulations to derive many other properties that don't depend on the electronic structure, okay? So for example, we can compute what is known as the phonon dispersion pattern and calculate the dot center. We can compute mechanical properties like the elastic constants and the bulk moduli. We can even do MD simulations using a foundational potential to get things like the ionic conductivity of a material from the simulations, okay? And we can do all this with a reasonable amount of accuracy, or rather a useful amount of accuracy, right? So I will never claim that they are more accurate than quantum mechanical methods, but they are accurate enough that we can do materials design and screening with them, and we can then move on to more accurate calculations for the things we really care about, okay? All right, so this was actually published in 2022. At that point in time, actually, we actually first submitted it to Science because we thought this was such a cool concept. The Science editors disagreed. They thought that this was actually not going to be of general interest to the community, okay? But in the end, we managed to publish in Nature Computational Science. Today, foundation potentials are a huge topic in academia and industry. There have been many developments since then. For example, there is other architectures like ChargeNet and Maze that came about a year or two later. There's also this effort from Google called the GNOME, or Graph Networks for Materials Exploration. That was published in Nature in October 2023. In October 2024, Meta themselves got into the game. They published this data set called the Open Materials 2024 data set, which comprises of about 100 million structures for training foundational potentials, okay? If you are, I'm sure a lot of you are aware that nowadays AI for material science is also a very big startup part of a lot of VC funded startups, and foundational potentials are unfortunately or fortunately part of the hype of way too many of these startups, okay? All right.
So question
now,
how in terms of understanding the difference between what the initial work, so it seems like the first project you said where you took the whole GFTs and you kind of interpolated between them using ML, but the second one, it looks like it's much more you're using final results to infer what dynamics must have been going on in order to produce the final results. Is that the shift?
Yeah, so I would say the first version, we were essentially training on DFT data, and then once we are trained on DFT data, we can simulate a lot of different material properties without having to rely on DFT, okay? We benchmark it against DFT, of course, but what we show is that there is no necessity to now do DFT. We can actually get a lot of these properties without ever having to do DFT. And we can do it for much larger systems as well, okay? Now, as for the works that come later, I would say they are architectural or data improvements in the sense that they explore different aspects of the architecture, like adding magnetic moments or spin. Maze is what is called an equivariant graph neural network. In other words, that has a certain preservation of symmetry in terms of the operations. The Google Gnome is basically generating a data set that is then used to further develop a potential that is quite a bit more accurate. And the open materials data set is just a data set, right? But they also introduce transformer models into foundational potentials, okay? But what I'm going to show you essentially is that the model architecture really matters not too much, okay? It is actually really more about the data that you train on, okay?
Okay, so that's interesting. So my question was going to be, to what extent are you capturing the invariance of the physics, the laws of physics? Because I'm noticing you have like 3 body, you can always get 4 and so on body interactions, which are approximations of the wave function. And now you're pointing to, well, maybe it doesn't quite matter what exact like physical priority you have as long as you have enough data. So
no, I think if you have the physical prior, it makes it easier to learn the fundamental interactions. But I would say we don't actually need to go to too much complexity. Even 3-body, I would say even the M3GNet architecture, which only has 3-body, the subsequent ones like Maze, actually they do capture 4 or 5-body interactions. It is not, it is an improvement, but it is not like a quantum leap improvement, right? In other words, there is some improvement, but not by a huge amount. So I would say that the physical priority does help. So the equivariant graph neural networks, they do converge a bit faster in terms of the energies and forces. So it does help the learning. But fundamentally, the final accuracy is not that much of a difference. Okay.
So then what should we be thinking as the frontier? And maybe this is a question for the end too. Is it the more heterogeneous materials, more higher temperatures where you have a lot faster interactions, so speed of light or speed of sound propagation matters? Where would be like the challenges then?
Yeah. So I'll get to that in the one of the final slides. Okay. So yeah, because it's also somewhat related to where we what we did subsequently. Okay. So all right. So so the next part of my talk is really on foundational data and software. As I mentioned, it is really about the data, not the model architecture. So no matter which of the foundational potentials you look at, like M3GNet, ChargeNet, or Maze, all of them are trained essentially on the MP relaxation data set that was derived in 2019. We derived a subset. Subsequent people use the entire data set. Okay. The problem with this data set is it has always not been the aim of this data set to be used for training machine learning interatomic potentials. Okay. This data set was basically just there, right? And the data set is very noisy. There's lots of errors in the energies. And because of all these errors in the energy, you actually get systematic errors in the foundational potentials that are trained on it, right? This is actually what that was done by Deng in 2024. He showed that most of the foundational potentials actually have this under prediction of the phonons, right? So there's a systematic under prediction. Now, so this is essentially the problem with the noise in the data. There is also, in my view, right, this problem where because big players like Meta is coming into play, they have unlimited compute, right, essentially. And they are essentially generating these data sets of 100 million data points, and they are building models which are 10, 20, 30 million parameters, right? So this is actually the trend in the number of the training data size and the model parameters. Yes, you do get improvements in accuracy as you crank up the training data size and model parameters, but you can see that even at 1 order of magnitude fewer data and model parameters, you are essentially getting quite good accuracy, right? So this bigger is better trend in the foundational potential, I would say, field is a bit troubling because it sort of defeats part of the purpose why we build foundational potential in the first place, which is we want a low-cost method that can simulate very large systems and a lot of materials, right? All these models that are very, very large, they are very expensive in terms of inference time. They are also super expensive in terms of training time, okay? So in just about February this year, we released what we call a MAPPAS, which stands for Materials Potential Energy Surveys data set. This is basically just a relatively small data set compared to the ones that you've seen before. It's about 400,000 structures. We improved the data, not in terms of the in terms of sampling. We basically developed this sampling method that we call direct sampling, where we essentially do encoding and PCA, dimensionality reduction, and stratified sampling of structures and atomic environments, such that we actually arrive at a very good, diverse data set, okay? Now, with that data set, we also do very, very accurate PBE and R2 scan calculations to actually get very high quality PES data. Now, for those of you who are not in the DFT field, PBE is basically the functional that has been used by in the community for, I would say, easily the past 30, 40 years, right? R2 scan is a relatively new thing. It came out about 5 years ago, and it is a lot more accurate than PBE in a lot of instances, okay? The only problem is that it's quite a bit more expensive, okay? But we were convinced that this is actually the right thing to do, because R2 scan actually provides significantly better predictions across a large number of materials, right? So this is just a show of the distribution of our MAPPAS data set compared to the OMAT24 by Meta. Ours is a lot more balanced in terms of both the low and high energy structures, as well as the low forces and high forces data, right? While the OMAT24 actually has a significant skew towards much higher energies and much higher forces structures. Now, what is more important is this, right? If you think of the training costs, if you are building a model using MAPPAS, we are really thinking about per epoch, about 15 minutes on one NVIDIA A6000. While if you are using OMAT24, which is 100 million structures, we are talking about 20 hours on 16 NVIDIA A100s, okay? So the training cost is on the order of a few $1,000s for training with MAPPAS, while it is on the order of millions of dollars with OMAT24, okay? So this is a simple question of efficiency, right? So not everyone has the budget or compute resources of a big tech company. So a lot of academics are more interested in this kind of scale. So of course, if scale does provide something, it's good. But what we show essentially in this work is that size is definitely not everything. We can train a TensorNet model, which is less than 1 million parameters, using the MAPPAS data set. That foundational potential is a lot more stable, and the predictions are essentially no different from what you get with the OMAT24 data set, which is 100 million data points, okay? So, yeah. Now, so that is for data. And in terms of data, subsequently, what we are continuing to build on the MAPPAS data set. I think, as Greg asked just now, what are some of the things that we are doing? We are also doing things like more higher temperatures generation of data. We're also building new architectures that can incorporate things like atomic charges on the atoms, which are important to model reactivity. So in other words, we want more physics and we want more diverse data, okay, either in terms of chemistry or in terms of the local environments, okay? What we don't want is basically essentially architectures that are just adding more and more parameters without adding more physics, or data that is essentially just brute force generation that doesn't really increase the diversity of local environments or information that we have, okay? All right. In terms of software initiative, I'm going to go through this fairly quickly. We have two. One is called the Materials Graph Library. This is actually a collaboration with Intel Labs. It's essentially a graph deep learning library for material science. It implements a lot of the latest foundational potential architectures, such as M3GNet, ChargeNet, and TensorNet. MetCal is actually the more interesting one that I want to talk about. It is essentially a materials calculator, right? it turns out that to compute a lot of different material properties with foundational potentials is actually a fairly involved process, especially for people who are not in material science field, or at least not in the computational material science field, right? So our aim with MacCal is really to provide a simplified and consistent interface to assess a lot of these properties with just any MLIP, okay? Just to show you what you can do with MacCal today, with just like 3-4 lines of code, you can get all these different properties from any foundational potentials, things like the elastic constants, the minimum energy path, which is important for diffusion, the equation of state, the phonons, whether it is in the harmonic or enharmonic approximation. All these things you can do it with very, very few lines of code, okay? And we are also building a benchmark based on these multiple properties, which we believe is much more important to benchmark against rather than just simple energy and forces, okay? All right, finally, I want to talk about applications and perspective. In other words, I mean, all that, so far I've covered things like architecture, data, and software. All those mean nothing if we don't really create any real world impact with foundational potentials, okay? So again, I'm going to focus on just one, mostly on one application, which is solid electrolytes for all solid state batteries. Now, if you are designing a solid electrolyte, you are interested in quite a number of properties. You need to balance between things like phase stability, electrochemical stability, ionic conductivity, electronic conductivity, and mechanical properties, okay? Now, it turns out that almost all these properties, except the electronic conductivity, you can actually get from any parameterization of the potential energy surface, okay? So phase stability and electrochemical stability is just a function of the energy. Ionic conductivity is, you can either get it from MD or you can do NEB calculations. These are all potential energy surface based simulations. Mechanical properties, again, is just the Bout and shear modulus. You can get it from a potential energy surface. The only thing you can't get is electron conductivity. For example, you need a band gap. This you can actually do DFT, or you can also use some other AI models that are trained specifically to predict the band gap of the material. And those we actually have a fairly good handle on, okay? Now, just to show you some of the things, exciting things that we have been doing recently. So for example, today we can use foundational potentials to predict real world synthesis conditions, okay? So this is one of the main big gaps between computational materials and experimental materials, okay? Very often people just do computational materials and they say, oh, I think this new material may potentially be interesting for this application. Experimentally, why don't you just throw a few things together and hopefully we get the phase that we predict, right? What I show here is that with foundational potentials, we can now get much closer to predicting exactly under what conditions can a material be made, okay? So this is actually a phase that was discovered by my colleague, Shyue Meng, and her postdoc, is this sodium chlosoborate material. If you just do the DFT 0K phase diagram, it will tell you, nope, this material is actually not stable, okay? It's not anywhere in the phase diagram. However, if you use the foundational potential to simulate like the free energy at finite temperatures, you will see that this material actually becomes stable at about 650 Kelvin, okay? And this is essentially right smack in the middle of where our experimental colleagues actually managed to make this material phase pure, okay? So in other words, we are getting very close to being able to predict not just is this material potentially stable in a dynamic sense or in an energetic sense, but rather being able to tell the experimentalists, why don't you put A, B, and C together at this temperature, and hopefully we can make that material, okay? And that is huge, right? We are very, very close to predicting synthesis, okay?
So question, are you thinking of like a phase thing where the more the temperature, or something more like it forms bubbles, and that depends on the like connectivity of the molecules and like these fancier structural properties?
No, we are not thinking here. We are not looking at porous materials, but rather just a phase pure crystalline material.
So just like, will it form a crystal of particular kind is the family of properties you're looking at?
Correct. Yeah. So in this particular case, yes. Yeah. This is a very, very recent work. This is actually a amorphous solid electrolyte. Now, I will say before machine learning potentials or foundational potentials, no one actually looks at amorphous electrolytes, or rather, very few people look at amorphous solid electrolytes in any computational sense. Okay, it's just very difficult to simulate them. But now we can actually say, well, since we have an amorphous solid electrolyte, can we optimize the ratio of the precursors that you use to make this amorphous solid electrolyte and see whether we can get higher ionic conductivity, right? And it turns out that we can, right? We actually find that if we adjust the X until about 0.5, we actually get a 1 order of magnitude increase in ionic conductivity compared to the base compound that everyone has been studying, okay? And this is not like it used to be. This would be maybe 5 years of work or at least 1 year of work, right? This is basically less than 1 week of simulations using the latest foundational potential that we built using MapPass R2Scan, okay? And I have not even begun to fine tune the potential, all right? So this is a work that is not yet published, but we are actually going to publish this fairly soon, okay? Now, our group is also now, we have foundational potentials. We can now essentially open up this top part of the screening funnel. We can now essentially not look at, say, thousands of materials, which is what we would have done during the DFT era. But now we can really explore millions of potential candidates and use a foundational potential to essentially do a preliminary screening of all the structures before we then maybe do more accurate DFT simulations to actually predict the properties of the materials before finally doing synthesis, okay? This just shows you some of the work that we have done in terms of comparing the predictions of foundational potentials in terms of electrochemical stability window. You can see that the top part is what you get with DFT, the bottom part is what you get with the foundational potential. You can barely tell there's any difference between the predictions, okay? In terms of ionic conductivity, we have this method of screening the ionic conductivity using just the mean square displacement at two different temperatures. And what we were particularly happy to see is that there are, of course, very well-known lithium superionic conductors, things like your Li10G P2S12 material, your Li3YCl6 material, and all the high conductivity materials are sitting in this good ionic conductor range. In other words, our foundational potential is giving at least very good qualitative result in terms of screening, right? So, and what you see is that there are plenty of these gray dots here. Those are essentially the materials that people have not yet explored as potential solid electrolyte for lithium-ion batteries. Okay. I also want to highlight that we have work that is in other materials, so things like high entropy alloys. There's this very, very work that I really like, where we essentially built a machine learning interatomic potential to start from DFT calculations to actually then do atomistic scale simulations, things like Monte Carlo and MD. And what this allows us to build is this composition dependent map of things like the unstable stacking fault energies. And then our collaborator then integrate all these statistics into their continuum-based dislocation models. And this is essentially a work that I like a lot because we integrate everything from the DFT scale all the way to atomistic scale to the continuum scale. Now, of course, in this work, we did it very manually. It's basically us passing data to and fro between different groups. But it is my belief that with the technology that we have on hand today, we should be able to automate this entire thing such that we should be able to do full-scale simulations from atomistic to from DFT all the way to continuum these simulations very, very soon. Okay. All right. This is my final slide. I just want to share some perspectives. So I think with foundation potential, some of the DFT era constraints have been broken. The state-of-the-art foundational potentials are already useful. Okay. I'm not saying that they are perfect. Obviously, they are not. But they are at the point where they are very, very useful and they can only improve. Some of the fine-tuned foundation potentials can provide improved performance for target chemistries. I want to stress that despite whatever company wants to tell you, whether it's a startup or not, that they have a much better model or much better data, there is really no data or model moat in foundational potentials. Okay, a lot of the data sets is already very good and they are all open source. Even if you manage to find some moat, some better model or better data, that's going to be quickly integrated, and you really don't have any moat there. I think that practicality is important. I don't really like the trend of going to bigger and bigger models and data. I think that we need right-sized models and data. More importantly, I think a lot of the algorithms and software that are being implemented right now, they are still not optimized for multi-CPU or multi-GPU simulations. That is critical. If it is not a very academically sexy project, but it is something that is very necessary for all these things to become a lot more useful. Okay. There's also more nuts and bolts stuff like writing workflows and softwares that actually can integrate foundational potentials, fine-tune potentials, DFT, high-level simulations, and experiments data in a very nice whole that allow us to do materials R&D in a much more integrated manner. Okay. And finally, I really would like to see more works on real-world materials design rather than just benchmarking and architectural developments. I think there's really a lot more scope to study real-world materials and multiple properties and discover actual novel materials. Okay, so if you go through a lot of the literature, when people claim that they discover a novel material, very often it is not a real discovery. It's really, I'm taking a sodium-containing compound, I'm changing some of the sodium to lithium, and that I call that a new material. Okay, so that is not in my. I mean, it is still a new material, but I'm more interested in really breaking that entire space. Right. For example, back in 2018, we actually did this without AI. We discovered a completely new compound in this strong-tone lithium aluminum oxygen space. That is a phosphor, right? This is an actual material that was synthesized, and we did this without AI. Okay. All right. I just want to acknowledge funding from the Department of Energy for the materials project. My collaborators, Christine Pearson. This is actually my group. They were, of course, the ones who did all the hardcore work. I'm basically the advisor, and I'm happy to take any questions.
Well, yeah, thank you very much. I mean, I have just one probably big one. I guess you're starting to go towards the dream where you have what, like a complex continuum system which has a bunch of chemical components, is deforming all the time, like a kite, or let's say if you were to simulate a kite that's deforming all the time due to wind pressures and has solar panels on it, and inside of that there's an electrolyte and it's doing photoelectric effect and propagating power to some battery. That's a giant pain, right? Especially as sun is beating down and then it's heating it up. So there's a lot of deep in there is DFT calculations and mechanical stresses from the very top and crop propagation in the middle. I guess for that dream, what is missing from the research community to make it happen?
So I would say the things that are missing is so we have connected part of the dots. So one part of the dot is basically, if let's say I'm simulating a new let's say solar panel, right? And the solar panel has a new material. I want to know what the mechanical property of that solar panel is. We are now very good at going from DFT to simulating the mechanical property of that new solar panel. But I think the connection between the atomic scale and the continuum scale, in other words, I want to simulate an actual real world solar panel. That part is still quite a black art. I know, of course, people are working on it in terms of developing machine learning models that can learn from atomistic simulations to actually fit parameters in the continuum model. So obviously, that would be one big gap. But I think a bigger gap is really the integration across scales, right? There's a lack of, I would say, integration in the sense that it's not like I can just press a button and it will go from DFT all the way to continuum scale, there's a lot of manual steps in between that I'm transferring data, or I'm having a human in between trying to refit stuff and that sort of thing. And I think that is something that needs to be addressed before we can actually reach the dream. So
makes sense. All right, cool. Yeah, let's say one more question, Jandra.
Yeah. Can we use DFT theory and other theories simultaneously to improve our accuracy?
yes, so we can. So there's this work that I didn't show where we essentially build what are called multi-fidelity models. So we incorporate, it's still DFT data, we incorporated both PBE and R2scan data. But what we showed was that we can actually build multi-fidelity models that allow us to learn from high-fidelity data, much smaller high-fidelity data sets, okay? So there is definitely methods to actually incorporate higher order methods, whether it is DFT or CCSDT or whatever methods that you want to use into the machine learning models. So I think that one is actually, I don't see that as being too difficult. So.
All right, fantastic. Okay, well, fine. Achid.
Hey,
Yeah.
hello.
Yeah.
So thank you for the wonderful talk. It was really enlightening.
Thank you.
My question was this: that we generally see that simulations, like simulation-driven approaches, are relatively limited for polymer composite type systems, right? So what? Because I mean, the main problem is that when you put composites in the polymers, it becomes really hard to predict what their properties are going to be. So how can foundation potentials or any other, like, what are your thoughts on that space in terms of addressing it with simulation?
Yeah, great. Yeah, great question. So I would say in the DFT era, definitely simulating a polymer is, well, not many people do that simply because it's way too expensive. But with foundational potentials, I think definitely, like I say, I'm looking at amorphous materials. Amorphous and polymers, yes, I would say somewhat close, much closer together, right? And the way I see it is that what you need is really not a foundational potential in that instance. I would say you will start from a foundational potential, and we actually have workflows that allow you to fine-tune the foundational potential for a narrower set of chemistries, or in other words, distilling down the foundational potential to a simpler model that is just as accurate or even more accurate for your polymer chemistry. Because in polymers, your number of different elements is not as large as 89 elements, right? You typically care about maybe 4 or 5 elements at most. So you can essentially distill down the foundation potential to a custom machine learning iterative potential that is at least 2-3 orders of magnitude faster. You will be able to simulate your composite. So, and this can all be done very automatically and very relatively cheaply, right? So,
perfect. Thank you very much.
Yeah, thank you very much. Yeah, well, this was a fantastic talk. Thank you for the presentation.
Yeah, thank you. Thanks, Greg, for inviting me. And yeah, happy to be here. And if you guys have any further other questions, I'm more than happy to answer them over email.